Hi there, welcome to another Calculus 1 video. This is the second video for section 311, and for some of you guys you don't really necessarily need to watch through this. This is just a couple more examples worked outside of the ones done in the previous video. If you're clicking already and things are going well, then you may not need this video, but just wanted to give you guys a couple of extra examples. Alright, so for problem number 1 here, a rock is tossed into a pond and that creates a ripple that is in the shape of a circle. So if that radius of the circle is growing at a rate of 2 inches per second, we want to determine the rate of change of the area of the circular ripple when the radius is 1 foot. So we have a circle, kind of draw a little picture here maybe to get an idea of what's going on. I'll cheat and create a real circle. Alright, and so the radius of the circle is given by r. The area, of course, of a circle is pi r squared. And so here both area and the radius need to be thought of as functions of t. Time is the independent variable, and area and radius are changing. You drop the rock in the center here, and our radius is growing. It's moving out, and as that happens, obviously the circle gets bigger and bigger and bigger. Okay, that's the idea. So let's see what we have given. The radius of the circle is growing at a rate of 2 inches per second. That's a rate per second. It says rate. That means it's a derivative. Well, it's the radius changing, so dr dt then would be 2 inches per second. And then we want to determine the rate of change of the area. And so we want to find dA dt when the radius is 1 foot. And be careful, this is inches, this is feet, so I need to make sure that they're on the same units. Either change that to inches or change this to 1/6 of a foot, either way. Okay? So what do? We take this area function and we differentiate it with respect to t. So we're going to take the derivative with respect to t of a. We're going to take the derivative with respect to t of the other side, pi r squared. Pi is just a constant. So the derivative of a with respect to t is dA dt. The derivative of pi r squared, bring down the 2, you get 2 pi r times the derivative of r, which is dr dt. Okay, so this right here, this is the implicit differentiation part. Okay, so if you're struggling with that part, then that's really a section 3.8 concept applied to this multivariable equation in which t is the variable that is changing. Time is changing, and that makes everything else change. Time is independent variable. Okay, so now I go back up here. My radius is 12, my dr dt is 2, and so I just plug it in. And I'm going to plug it in with units to help you see where units work here. So this is 12 inches. dr dt is 2 inches per second. And so if we multiply this all together, we're going to get 48 pi inches squared, inches times inches, per second. And that makes sense because this is indeed area per second. This is rate of change of area. Okay, so 48 pi is great if you wanted to do this and give me an approximation which would be appropriate for a word problem. You'd get approximately 150.8 inches squared per second. Okay, so you have to read what is being asked, whether it asks you to round to the nearest tenth or something like that, or if it asks you for an exact answer. This is the exact answer. Here we'll round it off. Okay, my math lab will direct you in that, and so will I on quizzes or whatever. Okay, but typically word problems we do give rounded off answers. Okay, that's the only time we do it. But all right, so let's try another one. Example 2. Coffee is draining out of a conical shaped filter at a rate of 2.25 cubic inches per minute. The filter is 5 inches in height and has a radius of 2 inches here at the maximum part. Determine how fast the coffee level is dropping when the coffee is at a height of 3 inches. Now the first thing to know is that I don't expect you to know the volume of a cone formula. It's 1/3 pi r squared h. where R is this radius, wherever you are, and H is the height. So if you wanted to find the volume of the entire coffee filter, then you just plug in 2 and 5 for R and H, but that's not what we're doing, right? We are looking into the rate of change of the height, determine how fast the coffee level is dropping, right? That's dHdt. And if it's dropping, then we expect it to be negative. So we want to find dHdt, and we're told that the height is 3 inches. So this is 3 here. That's how much coffee's left. Okay, well, all cones have a straight edge on the side, and this is thought of as a straight line. And so there's a ratio between R and H. Using similar triangles, R and H is the same as 2 over 5, which tells me gives me a formula for R when H is 3. If H is 3 inches, then R would have to be R over 3 equals 2/5. And so that means that R would be 6/5 inches. So I know R, I know H, but I'm looking for how fast the level is dropping, which is dHdt. So since I have this relationship between R and H, I'm going to want to plug in here because I don't want to get a dr dt and a dHdt because I don't know anything about R specifically. All right, so we want to use this relationship. R is equal to 2/5 H. Plug that in, and we get 1/3 pi 2/5 H all squared H. We want to get the volume down to one variable if we can. Sometimes we can't, but and then we do a product rule, and that's okay. But so 2/5 squared is 4/25 times a third is 4/75 pi. H squared times H is H cubed. So this right here is my kind of specialized volume function for this particular filter for this problem. Okay? So what are we going to do? We're going to differentiate with respect to T, V. We're going to differentiate with respect to T, 4 over 75 pi H cubed. And so we get dV dt equals 3, bring down the 3, 3 times 4 is 12 over 75, and that reduces to 4 over 25 pi H squared. And then, of course, we get the dH dt. But what are we looking for? We're looking for dH dt, be careful. So what is this value? 2.25 cubic inches per minute. Cubic inches tells me we're talking about volume. So this is dV dt right here. So we're going to plug that in. 2.25 equals 4 over 25 pi. H is 3 inches squared, and then dH dt is what I don't know. Okay? So we simplify this over here a little bit. We get 2.25 equals 36 over 25 pi dH dt. So if I divide both sides by this, that's 2.25 over pi times 25 over 36. That equals dH dt. And again, we're just going to plug that into my calculator here and figure that one out. 2.25 times 25 divided by pi and divided by 36. And you get approximately 0.5 inches per minute for this value here. That's dH dt. And it's understood that this rate of change here is negative. Why is it negative? Well, coffee is draining out. So technically this dVdt was negative, but because they asked for how fast is it dropping, I didn't need to use a negative. So if I would have used a negative for dVdt, I would have got a negative answer here for dH dt, which would have been fine, but then my actual answer is it's dropping at 0.5 inches per minute. So because the dropping was already listed, that gave you the negative idea, but it is being drained out, so that really is a negative rate. And again, inches per minute, if you would have used units throughout this, you would have come up with inches cubed canceling out with square inches, and then you would have had inches per minute. So if you need some help with the units, use your units throughout. If you're talking about change of height, you know it has to be inches per minute based on the context of the problem, okay? So hopefully those two problems give you a little bit more of a context and a couple of more examples of the type of thing that you're expected to do for this section. As always, if you need more help, reach out and we'll get you taken care of. Okay, thanks.